This is the first of two lessons to cover the topics in Chapter 18 of Entropy, Free Energy, and Equilibrium. This is a natural progression from Chapter 6, which studied the first law of thermodynamics and various ways of determining delta H for a particular chemical reaction, or enthalpy. In this chapter, we look at the second and third laws of thermodynamics and how they're connected to determining the spontaneity of a reaction. So just a quick review. The first law of the thermodynamics is that energy is conserved, never created or destroyed. And so out of that comes the fact that when you have a chemical reaction, if there is an energy change because of the chemical reaction, the energy is either transferred as heat or as work. So in that way, the energy is maintained. We also looked at the definition of enthalpy, which was the change in energy plus the pressure times the change in the volume of a system, and we connected that to the first law. Now, the main idea of this unit is to be able to determine whether or not a reaction is going to occur spontaneously. And when we say spontaneous, that means that it's going to occur without any outside intervention. So when you put the two things together, they're going to react with one another. Now, this does not necessarily mean if a reaction is spontaneous, it doesn't necessarily mean that the reaction is going to occur rapidly. That's why kinetics and thermodynamics are discussed in tandem, because there are 2 points of consideration. One is to consider whether a reaction can occur without any outside intervention, which is thermodynamics, and the other is to study whether or not a reaction can occur at a reasonable pace, which is what we study in kinetics. So for the most part, exothermic reactions tend to occur spontaneously because the energy of the system is decreasing, and that is a favorable process. So if you think about a ball rolling down the hill, it's going to have a tendency to do that, to go from a higher energy point to a lower energy point. And there's no outside intervention needed in order to make that happen. Now, we said that they have a tendency to occur spontaneously because what we're going to investigate is that enthalpy, or the change in H, is not the only thing to consider when we're looking at spontaneity. The other thing that we need to consider when we look at spontaneity is entropy. And our understanding of entropy has developed, and it came partly, our first investigation of the idea of entropy came from the fact that there are processes that occur spontaneously that are also endothermic, and this was curious to scientists. So if you look at something like melting of ice, going from a solid to a liquid, it's an endothermic process, so you require heat in order for that to happen, but it occurs spontaneously. Something like dissolving certain salts in water, they're endothermic processes, but these also can occur spontaneously. If you think to the reaction that I showed you with ammonium nitrate and barium hydroxide, that's the one with the two solids, and we put them in a beaker, and that reaction occurred spontaneously despite it being quite endothermic. So there's another factor to consider when we look at the spontaneity of reaction, and that is entropy. And entropy is when you have an increase in entropy, it means that there is more disorder in the system or greater randomness in the system. So these processes, evaporating, melting, dissolving, the reaction that you saw with ammonium nitrate and barium hydroxide, those are all spontaneous because of the fact that the entropy of the system is increasing, which is favorable. So just like an exothermic reaction is favorable because the overall energy of the system is decreasing, systems work towards increasing the disorder. So that is also a favorable process. Now, eventually what we're going to be doing is using what is called Gibbs free energy to look at these two factors together to decide whether or not a reaction is going to occur spontaneously. The rest of this lesson, though, is going to focus on entropy and deciding whether or not there's going to be a change in entropy, figuring out how to calculate entropy, and looking at the second and third law of thermodynamics. First of all, we want to define entropy. And entropy is a way of measuring the number of ways that a system can be organized. We're going to look at it pretty qualitatively at this point. So basically, if there is disorder, then there is entropy. And there are two different kinds of disorder that you can have. You can have positional disorder, which means that there's a number of different ways that the molecules can be organized. And there is thermal disorder, which is related to the distribution of energy among the particles. So the more random the distribution, the higher the entropy. Okay, which leads to the fact that when you have a higher temperature, you're going to have a higher entropy. So there's different things to consider when you want to decide whether or not there's going to be an increase or decrease of entropy in the system. You can look at the states. So if you've got a solid going to a liquid, there is greater positional disorder in the liquid. There are many more ways that the liquid molecules can organize themselves than in a solid. Okay, you can see there's much greater organization here. There's fewer options for how these molecules can organize. So liquid to a vapor is the same concept. Okay, in a vapor, there are many more ways that these molecules can organize themselves, which leads to greater positional disorder. Looking at the dissolving process, we've discussed this already, but if we can discuss it again here. So the solute and solvent compared to a solution. Okay, there are much more ways that the molecules can organize themselves when you've got the solute dissolved in the solvent than in the previous more orderly liquid and solid solvent and solute. Now, the temperature of the system also has an effect on the disorder. So the greater the temperature, the greater the thermal disorder. Okay, so that's going to be an increase in entropy. The other thing to consider is when you have a chemical reaction, you're going to look at the gas molecules before and after the reaction. So a reaction where there are greater number of gas molecules in the products, that's going to give an increase in entropy. If there's fewer gas molecules in the products than there are in the reactants, then that will lead to a decrease in entropy. And if there's no net change, then it could be positive or negative, but it's likely going to be a small number. Okay, so using these factors, you can look qualitatively at a system and decide whether or not you expect the entropy to increase or decrease. So for example, you've got a mole of ice versus a mole of water, and this is liquid water, and they're at the same temperature. So in this scenario here, because we're going from, sorry, in this question, it's asking for which one has the largest entropy. Okay, so in this case here, the one with the largest entropy is going to be the water, because there is, sorry about that, there is much more randomness in a liquid system compared to a solid. Okay, in this next example, we've got solid ammonium chloride and a solution of the salt in water. So a solution is going to have greater entropy. In C, just looking at a more practical example, jigsaw pieces are the completed puzzle. Okay, the jigsaw pieces have much more options for how they can organize, so they are going to have greater entropy. A pack of cards arranged in suits or randomly shuffled. Okay, if they're randomly shuffled, there's far more possibilities of how they can be organized than if you've got them arranged. Now, the second law of thermodynamics states that the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. Okay, so this is very important, and there are two things to consider here. First of all, it's the entropy of the universe that we're going to be looking at. The entropy of the universe includes both the entropy of the system and the entropy of the surroundings. So if we want to strictly use entropy in order to decide if a spontaneous process is going to occur, what we need to do is determine both the entropy of the system and of the surroundings. And if overall it's greater than zero, then the entropy of the universe is greater than zero, so it's going to be a spontaneous process. For an equilibrium process, okay, the entropy of the universe is equal to zero. And we're going to focus on equilibrium a little bit later. Our focus for now is going to be this idea here. So what we're going to be doing is determining how we can calculate the entropy of the system and how we can calculate the change in entropy of the surroundings, and then how we can obviously decide if a process is going to be spontaneous. Now, one of the things that is unique about entropy is that it's different from H in that you're going to be given the standard entropies, and they're going to be absolute values rather than being given the changes in entropy. So if you look at Appendix 3 in your textbook, you'll see the thermodynamic data for a number of substances. If you look to those, that's where we found our heats of formation. And our heats of formation were the enthalpy of a reaction forming 1 mole of the substance from its elements. And so we were looking at determining the change in enthalpy during a heat of formation reaction, and those heats of formation were reported in the tables. The units for those are kilojoules per mole. If you look in that same table, you can see the entropies are listed as S naught. Okay, so it's the standard entropy. The naught, as you'll recall, means that it's standard, so it's at 25 degrees Celsius and a pressure of 1 atmosphere. Now these entropies are absolute for that temperature. And we're going to discuss how that can occur a little bit later in the lesson. One thing to also consider is the units. The units for those are in joules per Kelvin per mole, okay, which we're also going to investigate as we continue through the lesson. Now, much like enthalpy, entropy is a state function, so it doesn't depend on the pathway. Okay? If we know the beginning and the end, we can determine the change in entropy. And as you see above, when we're determining the change in entropy of the universe, we're looking at the change in entropy of the system. So when we're studying a system, we do want the change. We want the difference in entropy between the reactants and products, and that will give us the entropy for the reaction or for the system we're studying. So much like the formula that we used, which was an application of Hess's law, we were able to find the heat of a reaction by taking the sum of the heats of formation of the products and subtracting the sum of the heats of formation of the reactants. Okay, we can do the same for entropy. So entropy is also, like enthalpy, an extensive property, so it depends on the amount of the substance. So when you are finding the sum of the entropies of the products and the sum of the entropies of the reactants, you do need to take into account the coefficients in the balanced chemical equation. Okay, so we're going to look at several examples.
Let's look at a few practice examples. In this first one, we want to decide if the entropy change in each of the following will be positive or negative. And then we also want to make a bit of a prediction about whether it's going to be spontaneous. And you'll see in a few moments that that can be difficult with the information that we have, but we'll do our best using our previous knowledge. So for the evaporation of 1 mole of ethanol, so if we're evaporating something, we are going from the liquid state to the gaseous state. And so in that case, there's going to be an increase in entropy. The gas will have more ways to organize itself, so the change in entropy is greater than 0. And as we know, at room temperature, ethanol will simply evaporate, just like water will evaporate. It will, it can take time, but when we're talking about thermodynamics and talking about something being spontaneous, it's not about how fast it happens, it's about whether it happens without any external assistance. So ethanol will evaporate. In the second example, this is a classic reaction we've seen multiple times where we've got magnesium reacting with oxygen. And we know that if we ignite that, then it will burn quite quickly. But we also know that magnesium will oxidize slowly over time. So this we can predict is going to be spontaneous, and we can think about it in terms of entropy as well. So here we've got a solid and a gas going into a solid. So in this case, we're going to have a decrease in entropy. So although decrease in entropy is not favorable thermodynamically, we can predict here, and we know from experience that this is highly exothermic. So this is a good example of a scenario where there is entropy, which is kind of going against us thermodynamically, but then we also have our enthalpy, which is, favorable in this case. In this example here, we've got a reaction of all gases. So we've got a xenon trioxide that's decomposing. So we've got 1 mole of gas, and then we've got 2.5 moles of gas. So in this case, we've got more gas being produced. So we'll predict that the entropy is going to be greater than 0. There's going to be an increase in the entropy with that more moles of gas. In this case, we don't know this reaction, so it's difficult to know whether it's going to be spontaneous. We can think a little bit and predict whether it's going to be an exothermic or endothermic reaction in terms of the bonds broken and bonds formed. But realistically with this one, we would want to use table values to calculate if we wanted to decide if it's spontaneous. In this last one here, we've got the dilution of an aqueous solution of sodium chloride. So it doesn't really matter what the initial and final concentrations are here. If we're diluting something, that's going to have more ways of organizing the ions in that bigger space. So the sodium chloride that's in there, now it has more options for how it can be organized. So we predict that to be an increase in entropy. And in terms of thinking about this spontaneously, we just think to ourselves, can we dilute, just in a lab without any external assistance, can we dilute a solution of sodium chloride? Sure we can. So we'll predict that this will be spontaneous. For these next examples where we're looking quantitatively, we're going to be using tables and our formula that we derived connected to the entropy values in the tables. So we know that to find the difference in entropy or the change in entropy at standard conditions, we're going to take the sum of the entropies of the products and we're going to subtract the sum of the entropies of the reactants. So you can see I've got my values already plugged in here. So I've got my values for my CO2, and then I've got 2 times the NH3 because it's an extensive property. So if there's 2 moles of NH3, we're going to have more entropy. Then we're going to subtract the values for urea and water. And when we're doing these calculations, it's helpful to kind of check our work by, in some ways, just by looking in advance and seeing, like, do we predict here that there's going to be an increase in entropy, or are we thinking that this is going to be a decrease in entropy? And so if you look at the states before and after, we've got a production of gas. So we're going to expect when we do our computation here to have a positive value, which in fact we do. We have positive 355.85, so that's going to be 0.9, but I'll do 0.85 because we're going to convert it to kelvins in a moment too. So joules per Kelvin. Okay, so those are the units for entropy. Remembering that when you're dealing with entropy, it's often a smaller value relative to our delta H values. The question also asks us to convert this to calories per Kelvin, and 1 calorie is equal to 4.18 joules. So to do that, we need to divide by 4.18, and we will have 85.1 calories per Kelvin. In this next example, we've got CaO reacting with hydrochloric acid. So we've got a solid and a gas producing a solid and a liquid. So we suspect in this case that there's going to be a decrease in entropy because of the changes in states experienced here. Products minus reactants, taking into account the coefficients. These are our values from our tables. And when we compute this, we get negative 230 joules per Kelvin. And I'll focus here more carefully on significant digits. So with the significant digits, because we are adding and subtracting our values, we are going to pay attention to the number of decimal places. And so this one here has no decimal places, so my answer has no decimal places, and I'm just going to put a point there to signify that it's exactly 230 that I want to show. This last one here, I've got C2H4 reacting with H2. I've got 2 moles of gas, and I'm producing 1 mole of gas, so I expect there to be a decrease in the entropy, which is the case. I end up with 121 joules per Kelvin. And it's 121.0 because of the decimal places there.
Now, recall that in order to decide if a system is spontaneous, a reaction is spontaneous, we need to look at the change in entropy in the universe. So we know how to calculate the change in entropy of the system. Next, what we need to do is consider the change in entropy of the surroundings. The change in entropy of the surroundings is directly connected to whether or not a process is exothermic or endothermic. When you have an exothermic process, you have heat being released. That heat is being released to the surroundings, and the impact on the surroundings is that there's a temperature change, and so the entropy of the surroundings is increasing. In an endothermic process, heat is being absorbed by the system from the surroundings, which means that the temperature of the surroundings is decreasing, which in turn means that the entropy of the surroundings is decreasing. Now, conveniently, because there is a direct transfer in that amount of energy, the entropy of the surroundings is equal to or proportional to the change in enthalpy. Okay, and it's got an opposite sign, okay, because if the system is exothermic, that means that the entropy is greater than 0, so we need the opposite sign to the delta H. Now, the other point to consider here is that the entropy of the surroundings will have changed differently depending on the starting temperature. So because the amount of temperature, the change in temperature is going to be inversely proportional to the temperature at which the heat is added. So what that means is if you start with something at 0 degrees Celsius and you add 100 joules of energy, that's going to have a different increase in entropy than a system that started at 100 degrees Celsius and 100 joules was added. The lower the initial temperature, the greater the effect of heat being added and the greater the increase in the entropy. So what this amounts to, because there's an inverse relationship, is that the change in energy of the surroundings is equal to the change in enthalpy over the temperature. And This also makes sense because, as you know from looking at the values in the table, entropy is reported in joules per Kelvin or calorie per Kelvin. Okay, so this is because the entropy is going to be temperature dependent. Okay, the other enthalpy, which we studied previously, was not temperature dependent. It didn't matter what the starting temperature of the system was in terms of the amount of heat that was added. Okay, so we have this important relationship here. Okay, so let's look at how this is going to be useful to us. In this example, we've got 1 mole of steam condensed from 1 mole of liquid water at 100 degrees Celsius, and we know that 40.7 kilojoules of heat is being released. We want to know what the change in entropy for the surroundings are. So the change in entropy for the surroundings is equal to the negative of the change in enthalpy divided by the temperature. So in this case here, heat is being released. So we've got an exothermic reaction. So it's negative of negative 40.7, and this is in kilojoules. And the temperature of the system here is 100 degrees Celsius. We need to convert that to kelvins, so we've got 373 kelvins. So you see that you'll be left with 0.109 kilojoules per Kelvin, okay, which is a small quantity, and this is why we report our entropies in joules per Kelvin. So this is the change in entropy of the surroundings using the enthalpy of a particular process. Now I'm going to add another example to your notes here, and what we're going to do is examine this reaction, N2 plus 3H2 goes to 2NH3. And what we want to know, the question is this a spontaneous process? Okay. And we're going to use the change in entropy of the universe. Okay. If it's greater than 0, then this system is expected to be spontaneous. To find the change in energy of the universe, we need the change in entropy of the reaction, okay, which is our system. Okay, and we need the change in entropy of the surroundings. And we're able to determine both of these things. So we can use tables to find the change in entropy of the reaction or of the system, and we find that we have negative 199 joules per Kelvin for this reaction. And if you want to try this, all of these substances are gases for this reaction. For the surroundings, okay, we can find delta H using the tables. And we find that it's negative 92.6 kilojoules per mole. So to find the entropy of the surroundings, it's negative of the enthalpy per unit of temperature. Now, keep in mind your enthalpy is in kilojoules, so negative 92.6 times 1,000 divided by the 298, which gives us a change in entropy of the surroundings of 311 joules per Kelvin. So when you look at the entropy of the universe, We add the two together. So negative 199 plus 311, we get 112 joules per Kelvin. So overall, this system provides a positive change or an increase in entropy of the universe. Therefore, it is expected to be spontaneous. Now, that doesn't mean that this reaction is fast by any means. In fact, it's quite a slow reaction, but it can occur without any external assistance. The last thing in this lesson for us to discuss is the third law of thermodynamics. Okay, and this kind of gives a bit of an explanation as to why we're able to determine absolute entropies at a specific temperature. The third law of thermodynamics states that at absolute zero, the entropy of a pure crystal is equal to zero. So at absolute zero, what we're referring to is a temperature of 0 kelvins. And so that's minus 273 degrees Celsius. When we're talking about the entropy of a pure crystal equaling zero, what this means is that the motions are at a minimum. So when you've got a pure crystal, it's so cold that the particles are held in a certain position and their motion is virtually zero. Okay? And what this means is that there is only one way for the molecules to organize themselves at that particular temperature. When there's only one way to organize, that's the point at which we have an entropy of zero. Now, because of this, we have a 0 point. So for H, we don't have a 0 point. There's not a particular temperature where H is 0 for all systems. But for entropy, we do have this point. At 0 Kelvin, we have an entropy of 0. So it makes it possible for us to report the absolute entropies. Because what we can do is we can look at the change in entropy over a particular temperature. And so change of anything is equal to its final minus its initial states. So if we want to look at a change in entropy from this temperature, okay, to this temperature, our initial entropy is going to be 0. So what that gives us is the absolute entropy. So what we have here is a graph that's showing you the absolute entropies as a function of temperature. Okay? And this looks a little bit like when we look at a temperature with respect to time and we're doing a phase diagram. Okay, so I just want to connect that for you. Okay, in a phase diagram, you've got a solid that's being heated, and then at the flat points, this is where your phase changes are occurring. So the energy of the system is not changing, okay, during the phase transition, because all of the heat that's being added during the phase transition is being used to change from a solid to a liquid, for example. The opposite is true for entropy. During a phase change, the entropy undergoes a sizable increase. So the entropy increases gradually as we are, a solid over a range of temperatures. And then when we're going from a solid to a liquid or we're melting, there's a sizable increase in the entropy, which makes sense because during melting, that's when we are providing an opportunity for more ways for the molecules to organize themselves. So the entropy is going to increase significantly. Then it increases gradually, okay? And then during boiling, the next phase change, you're going to have a sizable increase, and then it increases gradually again. Okay? What this shows, though, is that increasing the temperature increases the entropy. Okay? There's a positive relationship between those two things. So that concludes our discussion of entropy. Okay, just to recap, it's important for you to be able to compare two substances and decide which one has greater entropy. Look at a process and decide if that process is going to have a change in entropy that's positive or negative. You need to be able to calculate the change in entropy for the system or of a particular reaction using the sum of the entropies of the products, subtract the sum of the entropies of the reactants. You need to be able to calculate the change in entropy of the surroundings, okay, and of the universe by combining the initial two calculations. Okay, it's also important to understand that for a spontaneous process, the change in entropy of the universe must be greater than zero in order to follow the second law of thermodynamics.